Good morning, everyone. I'd like to welcome you to day 2 of our summer school on condensed matter physics, the theme being magnetism and quantum materials. Thanks for everyone who attended all the sessions and poster sessions yesterday. Hope you're looking forward to some more great talks today. A few logistical things. A reminder that we won't have any presentations tomorrow because of our hashtag shutdown STEM initiative. You can see the emails about that. But otherwise, everything else is, the new agenda is updated online. Everything else should be pretty straightforward. So another reminder is that if you have questions during this talk, just add them to the Q&A box at the bottom. And we will try and field as many of those questions as we can as soon as the speaker is done with his presentation. So without further ado, I'd like to introduce today's speaker. He's Professor Phuan Ong from Princeton. And he has a huge body of work in all kinds of different aspects of condensed matter physics, including high temperature superconductors, topological materials, and now quantum spin liquids. So tying into what Professor Balance talked about yesterday, Professor Ong is going to talk today to us about thermal transport in the spin liquid phase of alpha ruthenium chloride at low temperatures. So Professor Ong, I pass it off to you now.
Okay, can you hear me?
Yeah, it looks great.
Okay, good.
Share your screen.
All right, so good morning, everyone. Let me see. Okay, it's coming through, right?
Yeah, it looks great.
All right, so I hope everyone is staying safe in these unusual times. What I want to talk about today is really an experimental talk focusing on experimental issues and challenges in applying the thermal Hall effect to probe quantum spin liquids. This has been a long journey that started, maybe 15 years ago, but recently has become quite topical because of the strong interest, renewed interest in the nature of a quantum spin liquid. Let me first introduce my co-workers. My students are Peter, Tong, Max. Max is now at Riken, and the group led by Bob Carver, primarily Redan Zong, who's the postdoc at Carver's lab. And for the ruthenium chloride materials, we also collaborate with the Oak Ridge group and also University of Tennessee, Paige Lempenkelly, Arnab Banerjee, David Mendras, and Steve Nagler. All right, so in this talk, I'm going to be showing results, but I'll be mostly discussing the pitfalls and challenges in making accurate or reliable thermal Hall effect measurements. So I will talk about why we're interested, right, in thermal Hall conductivity, and then show some early results from Max on the terbium titanate. So this was the first inkling that there was something interesting that thermal Hall effect has to say about the very old problem of quantum spin liquids. Then some recent unpublished results on a new frustrated magnet found by Carver and Redan Zong. And then I will switch to ruthenium chloride. Okay, and I acknowledge support from the Moore Foundation, DOE, and NSF. All right, so the two mechanisms for conducting heat in an insulating magnet, we're not interested in conducting magnets in this talk. The two mechanisms, of course, magnons, which are spin waves, right, and phonons. And the idea is that hopefully by going to very low temperatures, we can de-emphasize the phonon contribution, although you can never quite suppress it. But by performing both the thermal Hall effect and the diagonal thermal conductivity called kappa XY and kappa XX respectively, you can hope to extract the contribution from the spin waves. Now, this is for an ordered magnet, right? So in order to have spin waves, you need the stiffness, the rigidity in an ordered state. So you need an antiferromagnet or a magnet, right? The new focus is what about quantum spin liquids, right? Or frustrated magnets. And there we are in really, we're completely ignorant about the landscape because there are no exact solutions for quantum spin liquids, although there are few now in zero field. One has a very hazy notion of what the excitations are. And here's where transport can really bring the issue into sharp focus, right? Because when you perform transport, you are really probing the low energy excitations, and then you apply a magnetic field. You can see how you perturb these excitations and learn more about their nature. And if they are truly quantum, right, then you can hope that they may show quantum transport behavior. So this is a wide open territory, right? Because the application of thermal transport to quantum spin liquids has only begun in the last decade or so. Okay, so very early evidence that if you had a ferromagnet, that you can actually see a thermal Hall effect from the magnons. I think the first evidence was from Tokura's group working with Nagaosa. But this is not a quantum spin liquid, right? This is an ordered magnet. Still, they showed some evidence that the magnons, in fact, can generate a Hall effect. Okay. Now, our interest was perked by some theoretical work from Patrick Lee and Nagaosa that, in fact, spin liquids may, in fact, display a very large thermal Hall effect, which sounds a bit counterintuitive. And in fact, when Max and I started to think about this, we couldn't quite convince ourselves that this is a realistic project. But anyway, so Max succeeded brilliantly. And so this, we think, is the first report of a large thermal Hall effect in a frustrated magnet, quantum spin liquid. Now, these three cartoons are sort of to guide your thinking, right? If you have a charged particle in a magnetic field, it executes a cyclotron orbit, right? This everyone knows. So you might believe then that the charge current can be deflected sideways by a magnetic field, and that in fact generates the Hall effect. But if you had neutral excitations, you have to think harder, right? In fact, it's sort of oxymoronic to talk about thermal Hall effects for a neutral excitation. So as an example, in a system with all spins down ferromagnet, an excitation could be a spin wave packet, right, with this cartoon sketch, traveling in this sea of down spins, right? And it's neutral, so it doesn't know whether to deflect right or left in a magnetic field. There's no right-hand rule, right? So that's why it's oxymoronic. How can you even pose the question, right? And so this seemed like a showstopper. However, if you had a chiral antiferromagnet, for example, here I show a Kagome lattice where the local moments are tilted with a solid angle that has some chirality, you might believe that the magnetic field could in fact determine the sign of this chirality, and therefore this could add a thermal current in the transverse direction. Anyway, so these were the kinds of ideas that were guiding the experiment. The system that we selected, because Kava had beautiful crystals of these pyrochlores, was the pyrochlore, terbium titanate here. So pyrochlore, let me remind you, is comprised of interpenetrating sublattices comprised of corner-sharing tetrahedra. So it's rather complicated, but if you look along the 1-1-1 direction, right, if you imagine staring down at this lattice in the along a body diagonal. It's a Kagome lattice, beautiful Kagome lattice, and it's layered, right? So this is the connection to the spin liquid problem. At low temperatures, some of the pyrochlores, this is an enormous family, something like 100 compounds, may show quantum spin liquid behavior. Prior to that, Art Ramirez had shown that actually if you go down to very low temperatures, some of them show spin ice behavior. So this is the famous ice problem, right? In water ice, the hydrogen has two equilibrium positions, and therefore in any formula unit, there is an enormous degeneracy, right? So each of the bonds, the hydrogen can either merge, either be close to one oxygen atom or the other. So when you talk about 10 to the 23 units, you obviously have entropy that scales like the volume. So this is called extensive entropy. And Ramirez showed that actually there's an enormous, this problem carries over to the spin ice problem, because the spin at each corner, the local moment at each corner can point either out or in, right? Exactly in analogy with the water ice problem. So the pyrochlore, some of them also have this extensive entropy. But now the quantum spin liquid problem is completely different, right? So it's not the spin ice problem. It's the inability of the spins to order magnetically because of geometric frustration. And I think Leon Balance talked at length about this problem, so I won't touch on the theoretical aspects. Now, let me remind you of a few perhaps obvious facts in thermal transport. So if you think back about charge transport, the electric field in a magnetic field, right, is given by the resistivity matrix, right? If you hold the current Jx fixed along the x direction, then you can back out the electric field simply by measuring the voltage drop in the longitudinal context. I think this everyone knows. You can then also infer the Hall signal by measuring the voltage drop across the transverse context, and thereby you can back out the resistivity tensor rho xy and rho xx. Then you have to invert this tensor, this matrix, and infer the conductivity. So the point of this is to remind you that you don't actually measure conductivity matrix directly. It's the resistivity that you measure, and then you have to invert the matrix to get the conductivity. So for example, the Hall conductivity is given by this very well-known formula. Now, the exact same reasoning carries over to thermal transport. The voltage now is analogous to temperature. The gradient of the temperature is in fact the analog of the electric field. And so what you are measuring, right, exactly in analogy with this, is you fix the current, the thermal current, JQ, which you produce by a heater here going to the bath. So you fix the thermal current and you back out the resistivity matrix, the thermal resistivity matrix. Unfortunately, most publications, because of historical reasons, do not focus on the resistivity matrix. Everyone just talks about the thermal conductivity, either the diagonal element or the Hall element, right? But don't lose sight of that, because you never measure the thermal conductivity directly. You have to infer it from the thermal resistivity matrix. This will be important down the road. So here's Max's early experiments. He had to convince himself that he could actually see a Hall signal, and he did so by carrying out several tests. The difficulty of thermal measurements is that you cannot switch the current direction in situ, right? Like you can in a charge transport, because there's no way to just throw a switch and have the heat current flow in the opposite direction. And this is a nuisance. So what Max did was mount two gold wires to the crystal, make the measurement with the heat going to your right, as indicated here. then warm the crystal up to room temperature, take it out, and then snip one of the contacts and join the other, and then have the thermal current go in the opposite direction. But this was essential because he had to convince himself, and more important, convince me that he was seeing a Hall signal. And the Hall signal is enormous. So you see here that the Hall angle ratio, this is basically the Hall resistivity divided by the thermal Hall resistivity divided by the thermal Hall diagonal resistivity, the thermal diagonal resistivity. So the Hall angle is very large. It's linear in field, right? So here's the field. And moreover, when you reverse the current direction, the thermal current direction, it changes sign, but it's otherwise identical. More importantly, he showed that in a analog material, which is the yttrium titanate, you notice that there are no local moments, no magnetic elements in this pyrochlore. Otherwise, it's identical. There's absolutely no Hall signal. In fact, Max increased the thermal current significantly, and he could show that this is down by a factor of 100, roughly 100. So the apparatus works very well. If there's a thermal Hall signal, he can see it with adequate resolution. I will say more about the experimental setup as we go along. So it's 1,000 times, sorry, it's 1,000 times larger than the analog. So we call this the vegetable, right? This is the sanity check, and this is the curve of interest. And so once we have that, so Max could make measurements at all temperatures, and you can see that it has a very strong temperature dependence. At low temperatures, it remains there despite the fact that the entropy content is decreasing very rapidly. And you can create a phase diagram where you see that in the temperature versus magnetic field plane, the spin liquid phase, or the frustrated region, is shaded in black. And the more intense the shading, the larger the thermal Hall signal. So the thermal Hall signal is getting larger and larger as you come down. Unfortunately, the application of a magnetic field at low temperatures also kills the spin liquid phase, right? Because you're forcing all local moments to align. So this is the bane of quantum spin liquids, that the act of trying to see it actually is detrimental to the state. So here we cannot exceed roughly half a Tesla at 1 Kelvin. And this is in good accord with what's seen by neutron scattering, where they also see a similar crossover. The divergence of the signal as expressed as a thermal Hall angle is plotted here, and you can see this divergence as you go to low temperatures, but then eventually you can't go very high in magnetic field before you kill the state altogether. Okay, so this is very early work, and I just wanted to show the broad landscape of what the thermal Hall effect is capable of telling us. Now, the first thing to watch out for in thermal Hall measurements is what's called the Magnetocaloric effect. And this is probably well known to many of you who do low temperature experiments, but it's good to be reminded of the facts because of recent attempts to make thermal Hall measurements in what I call the poor man's technique. I'll say more about that later on. First of all, if you have local moments that do not condense into the an ordered state, they can carry a huge amount of entropy at low temperatures, right? So the common saying is that, if you take a paramagnetic salt of a thimble full, right? So let's say 1 centimeter cube, its heat capacity at 1 Kelvin is equal to 3 tons of copper, right? So it has as much heat capacity as a small car, or maybe even a medium-sized car that is made of solid copper. That brings out the incredible amount of entropy that is stored in local moments for a non-interacting system. This contrasts, of course, with quantum excitations that you're well familiar with. If they are bosons, phonons, let's say, the heat capacity is severely suppressed at low temperatures. And for fermion electrons, it's suppressed as well, right? So local moments, by contrast, don't really care about quantum mechanics, right? Even at 1 Kelvin, each spin carries at least log2 of entropy. And when you change your magnetic field or the temperature, they release all that entropy or they absorb it. And this is something to really watch out for. So this is used, of course, in what's called magnetic refrigeration. And you can actually get down to 1 millikelvin. A few words about that. So the entropy, you can easily calculate the entropy for, let's say, spin half using very elementary StatMag, right? Non-interacting. And you find that it's a function that decreases monotonically. But importantly, the entropy is only a function of the Zeeman energy divided by temperature, right? Because there's no other energy scale. So it scales like h/t. So these two red curves taken at different fields are really the same function, right? So h2 is larger than h1. Therefore, it's the left curve with the scale radically expanded to the right, right? Okay, so you start with the system at a temperature and field, let's say here, and then you cool it isothermally, right? You have lots of helium exchange gas so that it can exchange temperature, heat flow with the environment. And so what happens is that when you increase your magnetic field, H2 is larger than H1, you drop down to the second curve, right, because of this scaling. And so you're releasing a huge amount of entropy, and this has to go somewhere, so the exchange gas pulls it out and gives it to the bath. So that's isothermal process. Then when you reach equilibrium, you then decrease your field back to H1, right? Let's say H1 is 1 Tesla, H2 is 5. So you go from 5 to 1 Tesla. But now you pump out, before you do that, you pump out all the exchange gas, so it's not adiabatic. So the sample has no way of changing its entropy. So when you decrease down to this second curve, it has to cool, right? Because of this, scaling form. And therefore, the temperature drops by itself to the temperature appropriate to the first curve. So you see that you have effectively cooled the salt simply by running the field up and then bring it back down, right? So by repeating the process, you can actually reach 1 millikelvin. So this is the earliest refrigerator capable of reaching 1 millikelvin. Now, the reason for telling you all this is because when you work on magnetic materials at low temperatures, you see a ton of entropy come out of the sample or absorb into the sample, depending on whether you're increasing or decreasing the magnetic field. So the procedure that we adopt in our lab is to pulse, is to step the magnetic field, right? So let's say I want to run the magnetic field up from 0 to 15 Tesla. You do it stepwise, right? Every time you step the field up by maybe a few hundred Gauss, right? And then you find that if you monitor the temperature, so here's the sample with 3 thermometers, A, B, and C. The traces are shown as a function of time. And all this jaggedness comes from the magnetocaloric effect. You see these spikes, and I want to explain to you what these spikes are. So I'm going to blow up the region in the dash box over here, and you see what's happening, right? So let's look at this first. When you step up the field, you find that the sample is actually emitting huge amount of entropy, and this entropy is so large that the phonons have a hard time equilibrating, right? So you have to wait a few seconds in this case before the system relaxes back to equilibrium. So this is highly non-equilibrium on account of the huge amount of entropy released. So you always have to wait for equilibrium. Otherwise, you are measuring a non-equilibrium effect, right? And now then why do you, when you cross zero field, do the spikes go away? Well, the reason is there is another effect, right? And this is very well known. So every time you change the magnetic field, your brass base plate is undergoing heating by the eddy currents. So the eddy current heating is either adding to this increase in entropy, right, worsening the magnetocaloric effect heating, or it's canceling it. So when the field is decreased by going from the negative to zero, you see that the spins absorb entropy, and the absorption is so much that it competes very well with the eddy current. So you just see a little glitch, right? Because there's no exact cancellation. You can see that the bath, which is a big chunk of brass, is actually being pulled up by this tiny crystal. The crystal is barely, a speck, right? Fraction of a millimeter in width, but it's generating so much entropy that it's pulling the bath with it. So it's a very impressive amount of entropy that's released. Now, because of this, you should not do these measurements in non-equilibrium configuration by, say, holding the field fixed and cooling the sample from room temperature, right? Because this is always non-equilibrium. There's no way for you to profile your field or the temperature to make sure that you're in equilibrium. So this is a very important point, and not paying attention to it has led to a lot of false reports, false sightings of the thermal Hall effect in the recent literature. Maybe I'll return to this later. Okay, so some recent measurements on a new candidate quantum spin liquid. So Bob, who is the fountain of many strange quantum materials, every few months comes up with a new system to study. These are beautiful crystals grown by Ridan Zong, and the measurements were done by Tong Gao. Here's a layered system that's based on cobalt, and the local moment occupies a triangular lattice, which is very large. So here's the layered nature. The triangular lattice is in the magenta layer, right? It's basically octahedra tilted onto its side, and the blue octahedra here are where the cobalt ions sit. Here's a top view, right? And you can see that it's occupying a triangular lattice, but the cobalt exchange is mediated by a super exchange, right? It's going through two oxygen atoms, as shown by this yellow line. So the exchange is very weak. So this system is almost paramagnetic, but it orders. In zero field, it orders. And sorry, I said it wrong. It doesn't order even down to 300 millikelvin. So it's always frustrated. The thermal conductivity here plotted as kappa XX. So again, to bring in the point made before, we measure the thermal resistivity matrix and then invert it to get both the thermal Hall effect and the thermal conductivity versus magnetic field. It shows that at low enough temperatures in zero field, there is a very rapid decrease of the thermal conductivity in zero field and approaches zero. So the system basically is approaching a zero conductance state at low temperatures. And we're still trying to figure out the physics of what's happening here. But as soon as you turn on a field that exceeds 4 Tesla or so, you recover a huge amount of thermal conductance, right? So there's a lot of interesting physics happening here that, as I mentioned, is still being processed. Okay, so this reminds you that you don't measure kappa XY directly. You actually measure the thermal Hall resistivity, and then you invert that to get this well-known inversion expression, right? So here we're showing the thermal Hall resistivity. And this illustrates a problem that we will come back to in ruthenium chloride. It turns out that within the region at low fields where we believe the spin liquid state exists, the thermal Hall effect is very large, right? And this agrees with Max's observation for the terbium titanate. It's very large and very temperature dependent. Here the temperature is being varied from 0.3 Kelvin to roughly 1. It's large, and but then once you start to suppress the quantum spin liquid state, it goes away, right? It dies. And above about 2 Tesla, we cannot resolve any thermal Hall resistivity because that is the signal and we cannot see it. So when you invert this matrix to get the thermal conductivity, you get basically large fluctuations here that don't have any physical, that are not reliable, right? You need to increase the reliability of the measurements by maybe a factor of 50 to get any information on the thermal conductivity, Hall conductivity at high fields, right? So that's why showing the thermal Hall resistivity is a much more honest way to tell the audience or the reader what your noise limits are, what your resolution is, right? So if you look at thermal Hall conductivity, be a little bit cautious, right? Because if the authors have not reported the thermal Hall resistivity, there's no way for you to judge how reliable the measurements are. Okay, so finally you can construct a phase diagram, and let me just focus on the color plot here. At low fields, you see what we call the quantum spin liquid regime in blue, and there's a very large thermal Hall resistivity signal. Once you suppress this interesting state by going to high fields, it's game over. Then it's just full of magnons on either side, and the thermal conductivity, kappa XX, is large, but there's no sign of any thermal Hall effect. So one take-home message here is that the spin liquid phase seems to have a large thermal Hall effect, but the magnons do not, right? So it's sort of the opposite of what one might have expected. All right, so let me now turn to the ruthenium chloride. And so here the 3 main players in my lab are Peter, Tong, and Max. And we are working with crystals grown and characterized by the Oak Ridge group. How am I doing for time? How much time do I have left?
You got about a half an hour left.
Okay, good. Okay, so I should speak more slowly. Okay, so this currently is a problem of intense interest because not only is it a quantum spin liquid, it's the first well-studied example of what's called a Kitaev spin liquid. And I think Leon probably talked about this at length. Sorry, I didn't listen to his talk. I was preparing mine, so I didn't have time to join the audience. But anyway, so just to roughly remind you, briefly remind you what's going on. So Kitaev found that if you had an unusual spin Hamiltonian, where you have an Ising, well, not Ising, Heisenberg spins along 3 directions, X, Y, Z, which are not to be confused with the lattice axis. I'll mention what the spins axes are in a little bit. And they had spin exchange that only involved, let's say, the XX component in one bond direction, and then Y and then Z, right? If you had this, which is extremely unusual and carefully designed so that Kitaev could find the exact solution, then you can solve for the ground state solution in 0 field. and Kitaev are using Majorana representation. So the Majorana is that you replace each spin local moment with 3 red Majoranas, which are called B's, and 1 in blue called C. Then you can solve this exactly, and the exact solutions show that the excitations from the ground state are either vortices called visons or these Majorana excitations. But this is for zero field. So in zero field, the system is gapped, right? Gapped to spin excitations. And Kitaev went on to show that you have edge states running in the perimeter. And that might give rise to the quantized Hall effect, quantized thermal Hall effect. But it's important to realize that the bulk is gapped to spin excitations, leaving chiral edge states that are ungapped. The neutron scattering folks have done a lot of measurements. So there's something like 30 publications, maybe more, mapping out the phase diagram in a field. And here I'm showing a cartoon of the phase diagram. At low fields below 7.5 Tesla, you have ordered state rather than a spin liquid state. And in the ordered state, it's comprised of zigzag pattern parallel to what's called the zigzag direction, right? So just like in graphene, zigzag means that, you know, it's going zigzagging here parallel to the field. And this is called the A-axis in ruthenium chloride. The perpendicular direction still in the plane is called the armchair, right? Why? Because, well, this looks like an armchair, right? So, I will be using these two terms just like in graphene. So the zigzag state is comprised of spins aligned along a zigzag direction, and they are anti-parallel between zigzag lanes. And there may be a minor phase slightly different from this here. But then above 7 Tesla in plane, parallel to the A-axis, you kill this order, and it's thought that this is now a frustrated spin liquid phase, right? There are no magnetic Bragg peaks here, and lots of interesting thermodynamic signatures. And if the field is too strong, you kill this interesting phase, as I emphasized before, and then you have this high field trivial paramagnetic state that has magnons and so on. Right. So in this tiny interval, that's where the physics of interest is. Now, although people call this a Kitaev spin liquid, the exact solution found by Kitaev doesn't apply, right? Because this is only in zero field. And theorists have been searching for the right way to approach this. And this is still a very intense area of activity. Okay, I think that's all I need to say by way of intro. Okay, a little bit more about the lattice structure as well as the spin axis. So here's a top-down view, right? I'm looking down along the C-axis perpendicular to the AB plane. And the ruthenium atoms define a hexagon. And it's customary to call the bond parallel to the B direction. Remember, B is the armchair and A is zigzag, right? They call it the Z bond. The reasons will become apparent in a second. And then the X and Y bonds are to the side of it. Okay, so the spin, so these are called the Kitaev spin axis, right? If you imagine the triplet spins axis anchored at any ruthenium atom, this is how you define it. You notice that there is a plane shaded in pink, right? This plane here. This plane, the normal to which I've drawn the arrow here, the normal to this plane is called the Z spin axis. So you see that it's not lying in the layer, in the plane of the layer, it's tilted upwards, right? And similarly, you have this blue plane here, and the normal to which defines the x-axis, and then correspondingly the green plane, which I haven't shaded, that's this plane here. So these three spin directions are mutually orthogonal, and they stick out of the layer. So these are called the spin or the Kitaev axis. It may be a little bit easier to visualize if you take one of these tetrahedra and you tilt it. I keep calling it tetrahedra, this is octahedron. And you tilt it vertically, and then the pink plane that I've shaded here becomes the horizontal plane. So the spin axis is perpendicular to this plane, right? So another way of saying this is that the bond, right, now come back to this bond, the bond perpendicular to the projection of the spin Z, the Z spin axis on the plane is called the Z bond. So it's a bit confusing, and for a while I was quite confused about about all these lattice parameters, right? So the bond that is perpendicular to the spin axis is itself called the Z bond. Okay. But the whole point of this discussion is that the 3D nature of the exchange is important. So there are maybe 20 theoretical attempts to solve the problem in a magnetic field, and most of them focus on the 2D nature of the lattice, of the spins. But we think that's a mistake. I think the Z coupling, the C-axis coupling is not negligible. In fact, it's quite important. Oh, I forgot to tell you. So this is an insulator. It's a beautiful insulator with an optical gap of 2 electron volts as measured by photo emission. And so at 1 Kelvin, there are no electrons around. So it's a completely insulating material. A lot of attention was heightened by the report by Matsuda, the group led by Matsuda in Kyoto, of the observation of a quantized thermal Hall effect. So here's some of the data, right? So this again is the cartoon of what the thermal Hall measurements involves. And I won't go through that because I've discussed this quite a bit already. And Matsuda has also drawn the excitations that are expected, right? These are called the Z2. The Z2 flux is the vortex that I mentioned, and Majorana fermions. So Majorana fermions supposedly travel along the edge, along the zigzag direction. These visons or Z2 vortices are in the bulk. The bulk is an insulator with regard to spin excitations, or at least that's the interpretation. So here's the phase diagram that I mentioned before, and the zigzag phase that the Kyoto group has drawn. Okay, so the data shows that in the region where the spin liquid state appears, between 7.5 Tesla to roughly 9 or 10 Tesla, the thermal Hall effect signal is finite and quantized. And okay, one can basically quibble about the fluctuation in the noise and so on, but there's something there, right? But the data stops at 4 Kelvin, right? And this has been a deep puzzle to many people, because quantization of a transport current generally gets better and better as you cool down to sub-Kelvin temperatures, right? As we learn from the quantum Hall effect. Here, there's absolutely no data below 4 Kelvin. Well, a shade below, 3.7, but that's where the data stops. And so it's sort of interesting. So that was the first thing that we thought that we should try. Well, also because both Kasahara, the first author, and Matsuda were former postdocs in my group. So we thought that we should also try what they've done. In a second follow-up preprint, which was released this year, they've shown that even when the field is tilted along the zigzag direction, A-axis, right? So the field is now parallel to the A-axis. You see a thermal Hall effect. And again, it's quantized. And it reverses sign when you reverse the field along the A-axis. So this is an anomalous thermal Hall effect, right? It's not, obviously the Lorentz force is not involved here, and there should be no Hall signal. But when it appears, it again appears within the thermal Hall, quantum spin liquid regime, and it approaches quantization, but now with a with more scatter. Again, there are no data below 4 Kelvin that we could see. Let's say, for example, here, right? It goes down to maybe 3.6, 3.7 and stops there. And what we did then was to extend the measurements down to 0.3 Kelvin, 0.35. So a factor of 10, right? And try to sort of match up to that data. Okay, so the crystals grown. All right, ruthenium chloride actually is a very finicky material. It's layered and it's highly sensitive to strain, right? If you abuse the crystal too much by flexing it, the dislocations introduced will broaden out the antiferromagnetic transition and introduce spurious effects that are not observed in the pristine crystal. So these are fairly large crystals of the size of millimeter or more, provided by the Oak Ridge group. And the way we mount it for Hall effect is that both the heater shown here with the orange bar, as well as the thermometers are heat sunk to the crystal, right, by thick gold wires that you see sticking out. And so you never attach the thermometer to the crystal. It's always sitting off to the side and supported by Delrin posts so that it doesn't shunt too much heat away. And for this particular crystal, it's along the A-axis. The field is applied along the A-axis. And here the crystal is being tilted at an angle, so the field is off the alignment with the layer. And again, here's the cartoon. The B and C thermometers measure the thermal Hall signal, whereas the A and B thermometers measure the diagonal kappa XX signal. Okay, so going on to the thermal Hall effect, when you go below 4 Kelvin, and this possibly was the reason that the Kyoto group stopped their experiments there, you start to see enormous hysteresis. As an example, we're showing here the thermal Hall signal, the diagonal conductivity signal measured with the field swept from left to right in blue, shown in blue, and then the return sweep from right to left. And you can see that there's a huge amount of signal. This is what we call the anti-symmetrized curve, right? So we have taken the forward sweep and the reverse sweep and anti-symmetrized them in a futile attempt to get rid of the hysteresis. So you can sort of see the kinds of experimental challenges. And here we have really taken this anti-symmetrization seriously. And you see that even if you do a very careful job with very high resolution, there's always a fictitious Hall signal, right? So I'm going to spend a few minutes talking about how we solve this problem. So the problem was actually encountered in the first experiments by Max Hirschberger, and he came up with this technique to get around it. So I want to explain to you the way I understand his technique, right? So here goes. All right. So remember, when you make a thermal Hall measurement, you pray that the thermal Hall contacts are aligned, right? That they are perfectly aligned in the transverse direction perpendicular to the heat flow. But of course, that is impossible to achieve. And if you have a very large variation in the longitudinal gradient, you will always pick it up. So alpha is the measure of misalignment. Alpha could be as small as 1%, which is already quite good, right? But if the longitudinal signal variation is 1,000 times larger than the Hall signal, then this will come true and dominate the Hall signal. All right, so let me explain what you observe experimentally. So this is what you measure physically, what you observe, right? That's the temperature difference remember, I said, do not use a thermocouple. Thermocouples are useless at this temperature range, and they tend to have very large field dependencies that are a nuisance. Totally unreliable. And this is the intrinsic signal that you're going to feed into your resistivity matrix, right? This is the intrinsic signal that you hope to disentangle. And here's the contamination due to misalignment alpha. And it becomes a problem when it's not only hysteretic, but it has memory, right? And here's a sketch of what that looks like. So now I'm just plotting what you see when you measure the thermal, longitudinal thermal difference along X, sweeping the field from negative to positive, which I'll call the forward sweep. You see the blue curve, and then when you return, you see the red curve, right? And the reason for this is either due to the motion of domain walls, right? Domain walls cause a lag between the magnetization and the imposed field, or it could be due to a weakly first order transition, right? If there's a first order metamagnetic transition, you will always see a lag, right? If you measure the thermal conductivity, you will see this, and that can dominate the intrinsic Hall signal. All right, so to fix terms, I'm going to call the blue curve the forward sweep, right? I'm going from negative to positive field. And then the reverse curve, I'll call delta star. So that's the reverse sweep. And I'll flag that by having a star there. It's not complex conjugation. It just tells you that I'm now sweeping from positive to negative field. So the system has a memory, and we need to get rid of that memory effect. Now, if this is a conventional hysteresis, let's say due to a good old ferromagnet, the intrinsic Hall signal will have this symmetry form. If you plot it, you take the red curve, flip the sign of its magnetic field, and then reverse its sign, and you will exactly recover the blue curve. Similarly, if you take the blue curve in the diagonal signal, change the sign of the red curve, right? So it now flips vertical about the vertical axis. It will coincide with the blue curve, right? So these two symmetries are important. Now, if you measure the reverse sweep, that's the red curve for the Hall effect, you will pick up both the Hall signal, which you would like, plus the contamination, right? But now you notice that if you manually change the sign in your computer of the recording of the signal, then you will get this. And then if you impose the symmetry that I mentioned in the yellow box, you can write this in terms of what you get in the forward sweep, right? So now you have this equation. And now if I repeat the forward sweep equation at the very first line down here, you notice that these two terms now are identical, and these two terms are also identical. So it remains to add and subtract them. In particular, if you desire the intrinsic Hall signal, you get it as the difference of these two curves. So this is Max's technique. In our lab, we call this the in-out, the in-in-out-out technique. But this, I think, is a clearer way to explain it, right? This is not the naive. Now, what if you did the naive thing, the anti-symmetrization? So here, if you assume a case where there's no Hall signal, zero, completely zero thermal Hall signal, then all you're doing is anti-symmetrizing this curve. And I think I need not convince you that you will just see a beautiful butterfly hysteresis. So for a long time, we were seeing these curves and not understanding why they were so distinct and unusual, right? So whenever you see a butterfly hysteretic curve, then you're doing something foolish. So as an example, if we took that butterfly curve seriously and convert it to thermal Hall conductivity, you see that below 3 Kelvin, you see a huge thermal Hall signal. This is all completely fictitious, right? And fortunately, we realized this before we wrote it up for publication. All right, now coming to ruthenium chloride, at low temperatures with the magnetic field parallel to the zigzag direction, we find that, even though the fictitious thermal Hall signal is very large, after using the technique that I mentioned, you see that the intrinsic thermal Hall signal is 0. And this illustrates the resolution of our experiment as well as the uncertainty. So using ruthenium oxide thermometers, we can actually resolve at 1 Kelvin changes of 50 microkelvin, right? Remember, the sample is sitting at 1 Kelvin. The temperature gradient across it is perhaps 100 millikelvin. We can resolve the transverse gradient to 50 microkelvin. This thanks to the heroic efforts of Tong and Peter, right, in the last couple of years. But that's not the end of the story, because there are uncertainties, right, that cause these ups and downs, right? So the 50 microkelvin is the width of the curve, and the uncertainties are plus and minus 150 microkelvin. Anyway, this gives an idea of how we can now push the measurements to very high resolution. No thermal Hall effect at all when the field is parallel to the armchair direction. However, in agreement with the Kyoto group, when we now switch the alignment to the zigzag direction, you start to see, okay, initially at 1 Kelvin, there's nothing. But at 4 Kelvin, you start to see appearing the black curve, a Hall signal. And this is very strange, right? The field is in plane, so there should be no Lorentz force. The system doesn't know what's right and what's left. Nonetheless, there is a thermal Hall signal, and it appears precisely where the quantum spin liquid is supposed to be. But one perhaps cautionary note here, when you exceed the peak, the thermal Hall resistivity dies very rapidly. So it's a struggle. It's a struggle to get, when you convert this to thermal Hall conductivity, the signal you're working with is dying very rapidly. So we cannot rely on the conversion above 10 Tesla. So we're converting all the thermal Hall resistivity to thermal conductivity now, and this is the curve we get. So right now, this is our best guess or determination of what is the thermal Hall signal below 4 Kelvin. So there's nothing below 3.3 Kelvin, and then it starts to increase, it starts to increase very rapidly with increasing temperature, and it soars well to very large values, right? And this constitutes the anomalous thermal Hall signal that the Kyoto group announced in their recent preprint, right? No thermal Hall signal when the field is parallel to the armchair. There is a thermal Hall signal in the quantum spin liquid regime when it's parallel to zigzag. Unfortunately, we do not see quantization, right? So here I repeat the data. We have checked our measurements against theirs. See, the data again stops at 4, a shade below 4 Kelvin. We are going down to 0.3, which will be way over here. Sorry, over here. And we're seeing that the signal systematically increases and then sails right through this quantization line, right? So if it's there, we could have missed it, right? So we are currently improving the measurement to see whether we've missed the quantization. But then if you step back a little bit, it's a very strange behavior for a quantized current, right? You don't see anything when you go too low. You don't see anything when you go too high in temperature. You have to be in a sweet spot. And that seems a bit too rich, too restrictive for a quantized value. So my current bias, I'm not sure it's shared by Peter and Tong, who are responsible for this data. My current bias is it's not there. It's not quantized. If you do it over a very wide range, it smoothly sails right through the quantization value. But as I said, more measurements are now in progress. Okay, my time is up. So let me just summarize the things that I've mentioned and bring out additional points. At low temperatures, a paramagnet, a free local moment, has a huge amount of entropy. As I mentioned, I compared a thimble full of material to a 3-ton car made of solid copper. They share the same heat capacity. So that's a sobering thought, right? So this amount of entropy comes out or is absorbed whenever you change the magnetic field or you change the temperature. It's pure thermodynamics. You cannot escape it. And it's a serious concern for all thermal Hall measurements. So if you adopt the poor man's method, which several groups have done to our dismay, the poor man's method is you hold the field fixed at, let's say, 7 Tesla and cool the sample from room temperature down to 3 Kelvin or whatever, and then take the Hall signal, warm it back up, reverse the field, and then cool it down again, and then you subtract. So this is a highly non-equilibrium experiment. You cannot do the kinds of step measure strategy to make sure you're in equilibrium. So all such measurements should be really looked at with a highly dubious eyes. Also, you cannot use thermocouples. Experimentalists know that type E thermocouples are the thermocouple of choice for low temperature because they're based on the Kondo effect, right? Basically, it's gold dissolved in iron, or the other way, iron dissolved in gold to give you a huge Kondo effect. But because of that, it's very field dependent. So it's highly unreliable. All my guys have tried calibrating them and basically just discarded them. Then there's a new concern when you look at magnetically ordered states. Hysteretic effects can lead to a fake butterfly thermal Hall signal unless you adopt the technique that Max unearthed. And it can be called time reversal or in-out-out technique. And this seems to effectively correct for all these hysteretic effects. When there's no thermal Hall signal, we explicitly see it as a 0 Hall signal. So this is something to watch out for. So currently the thermal Hall resolution is very good. We can, impose a 100 millikelvin gradient across a small crystal and detect 30 microkelvin transverse difference. So that's sobering, right? However, because of these uncertainties, extrinsic effects, we can only vouch for maybe 150 microkelvin uncertainty. But anyway, this can be improved as time goes by, right? So there's something to work on. Coming to ruthenium chloride, we agree with the Kyoto group that there's a thermal Hall effect with a field parallel to the zigzag axis, but there's no quantization. And so this needs to be worked out between me and my former postdocs, and we're gonna have fun doing that. All right, so thank you for your attention, and let me just show the co-workers again. Thanks for your attention.
Okay, thank you very much, Professor Ong, for a really great talk, really great experiments and some great explanations about all kinds of different techniques involving quantum spin liquids in theory. So we have about a dozen questions in the queue. So what I'm going to do now is read the questions aloud, and then we can just go through and answer them as normal.
Sure.
So the first question comes from Ashutosh Singh, which is, what is the origin of transformation of a classical to a quantum spin ice in dysprosium titanate and terbium titanate? So that's from earlier on in the talk.
Okay, so whether it's a quantum spin ice. Okay, so again, in spin ice, people talk about classical spin ice and a quantum spin ice, right? We don't think the quantum spin ice regime. Now we don't think that these two belong to the spin ice paradigm. We think it's not. This is not very well understood, but I think it's a frustrated system that doesn't have the spin ice character. Yeah.
Sure.
These materials, because they are so, the family is so broad, right? You can have all kinds of orderings depending on the magnitude of the exchange. So it's a zoo, and I'm not entirely familiar with all the different families within the zoo, but the quantum spin ice is now restricted to only a few of these titanates. I think ytterbium is one, terbium. So this should actually be a quantum spin liquid, not a quantum spin ice. Sorry, I might have misled you in going over this. Probably this question should be addressed to either Leon Balance or some theorist.
Sounds great. The next question is from Pavel Volkov, which is for sodium, barium, I guess phosphate, I don't know, cobalt phosphate.
Right.
What is the estimated value of the exchange, and what is the Curie-Weiss temperature from the susceptibility fits?
The exchange is very low, and the Curie-Weiss temperature is about 30 Kelvin, I believe. Let me go back a little bit. Yeah, so the estimated exchange, so there's some debate within the group about the best way to estimate that, but it looks like it's about 30 Kelvin. So it's a fairly small exchange and a small Curie-Weiss temperature. So what was the other question? I missed that.
Oh, I think that covered it, I think.
Yeah, so the frustration ratio, so this is the Ramirez ratio, right? It's about 100. So this is a fairly frustrated system.
Right. Sure. Another question comes from Pontus Laurel, which is what are the limits on how thin systems can be used in these thermal Hall measurements?
Well, it depends on the problem at hand. The thinner the crystal, the better, right? Because the way it works out in the thermal Hall measurement, you want to go for as thin as you can get away with. So we're talking about maybe 20, 30, 50 microns, right? Otherwise it gets so thin that you can't support it. Remember, you have to hang all these thermometers off it and the heater as well. So the thinner the better, but 50 to 100 micron is about the limit. In the case of ruthenium chloride, we find that when you make it too thin, it becomes even more susceptible to strain defects. So you can't go very thin with ruthenium chloride. We in fact now want to go to thicker crystals. So that makes the experiment harder, but we think that it makes it less susceptible to strain effects. Yeah, so the question is that there's no hard answer. It depends on the mechanical integrity of the crystal as well as the physics, right? Whether going to very thin crystals is detrimental to the physics.
Sure. A couple questions about experimental techniques. One is to extract the Hall resistivity by symmetrization, does one need to be able to apply a temperature difference along both X and Y directions?
No. The whole idea is always to, let me go back to the appropriate slide. I think it's probably slide 8. Yeah, okay. So think back about charge transport, right? So when you perform a Hall resistivity measurement, let's say a charge Hall resistivity, you're not imposing a voltage difference, either longitudinal or transverse, right? You are observing that. So what you're imposing is a current. So J is held constant, right? J is actually the current. And then the sample gives you the voltage difference in the Hall direction Y or along X, right? So you impose J, which is the quantity on the right-hand side, and then you measure the response. Yeah, so that's the best way to say it. The response of the sample is what you measure as the voltage drop. Similarly, in the thermal Hall measurement, you impose a heat current, thermal heat current JQ, and then the response of the crystal is along the Y direction, the thermal difference along Y and along X, right? So again, the right-hand side is what you impose, and the left-hand side is what you measure as the response.
Sure. Another question here is, the new measurement of kappa xy is not scaled by 1/t in comparison with the Kyoto's group. Is this quantization, is the quantization approximately restored if we rescale kappa xy by 1/t? And also physically, what causes thermal Hall effect in spin liquid phase in the pyrochlore compound? So I guess it's two different questions.
Let me address the first question, then have you reread the second question. So it doesn't matter whether we scale by dividing by t. So we have done, obviously, yeah, we have done all of that, right? Because it's a fairly trivial exercise to rescale, to divide by temperature and replot. But it's not, it doesn't depend on whether you, so in some plots you will see, like here we have divided by t. It depends on what you're trying to emphasize in your plot. But rescaling doesn't change anything.
Sure.
Yeah, obviously we've done that. So what's the second question?
Also, physically, what causes the thermal Hall effect in spin liquid phase in the pyrochlore compound? So I guess was the physics?
Oh, in the very first experiment.
I think so, yeah.
Yeah. So that is the $64 question, right? So the spin liquid phase, the excitations are basically unknown. Right. So one way to think about it is the following. Right. So here's a cartoon of the crystal, and we assume that there is a Berry curvature. Right. But now we're talking about Berry curvature that affects thermal transport. So you can think of all these bands, Magnon bands in the spin liquid. They're not Magnon's excitation bands. But there is a Berry curvature in some theories. And when you apply a magnetic field, the Berry curvature points up, let's say, right, in alignment with the applied field. So a spin packet, a wave packet, will be flowing at the boundary, and then it will experience what's called a Luttinger force. So Luttinger called this the anomalous velocity, right? So there will be an anomalous velocity given by the cross products of the boundary force, let's say gradient of the potential, crossed into the Berry curvature, omega. So the cross product of that gives you what's called the Luttinger anomalous velocity. And you can show that because of that, the velocity has opposite directions on opposite edges. And this is by far the most popular theory approach. So there are now 4 or 5 theoretical approaches. So all based on the existence of Berry curvature in a topological spin liquid. And that gives rise to this edge current, which gives rise to the thermal Hall effect.
Sure. A few more questions here. Analogously to geometric frustration rationalized by local spin systems, could frustration also be explained in itinerant systems by the competition between itinerant and magnetic states? Maybe that's a question for Leon or something, but.
Can you read the question again?
Sure. Let's see here. Analogously to geometric frustration rationalized by local spin systems, could frustration also be explained in itinerant systems by the competition between itinerant and magnetic states?
Yeah, I've never encountered any discussion of frustration in itinerant magnets. It doesn't seem possible because the notion of frustration, so that there are 2 mechanisms, I suppose, for frustration in magnets, right, that I know of. The first, which is the initial model, is due to lattice frustration, lattice geometry. Let me see if I can pull up the lattice. Oh yeah, okay. Hold on a second. So for this sodium situation, see for this triangular lattice, right? So if it's antiferromagnetic, then the local moment here is always unhappy, right? If it is anti-aligned with this neighbor here, and this neighbor anti-aligns with that, then these two will be very unhappy. So that's called geometric frustration. There is now, in the context of Kitaev spin liquid, also exchange frustration, but that again involves the lattice and local moments. So let me quickly go to the Kitaev situation. Oops. Yeah, so around a ruthenium, the fact that it has different exchange values along the 3 bond directions in a hexagonal lattice, that could also lead to frustration. So this is the newer kind of frustration. And I think those are the only 2 I'm aware of. When you have itinerant electrons, I don't think it lends itself to this kind of geometric frustration argument. But maybe the theorists would have a different point of view. So yeah, this should be posed to the theorists.
Sure. I think we have time for one more question, which is, does doping play a role in the phase diagram of ruthenium chloride?
Nobody, to my knowledge, has succeeded in doping it. If what you mean by doping is changing the carrier concentration, the gap is too large. But if you're wondering if doping can change the exchange, yeah, when you start to alloy or introduce other kinds of, let's say, 3D elements to replace ruthenium, you tend to rack up the lattice, and disorder then becomes a dominant factor, right? So at this stage in the game, we are trying to get as pure a platform as we can. And so, yeah, so maybe that will come later once we understand the physics well enough to start tweaking the lattice. But right now, we're trying to get as high purity a system as possible so that we can extract the transport properties.
Great. Well, thank you everyone for asking some really great questions. Sorry we couldn't get to all of them now. But hopefully some of them will be resolved later in the week. And thanks again to Professor Ong for a great presentation.
Okay, good. Stay safe.
Thank you very much. I'd like to invite everyone to our 1 p.m. and 3 p.m. webinars by Professor Amir Yacobi.